on to step 4 of our 4-step process. I want to talk about CNC heads and how we do things here at S&S. Our CNC head is essentially you take your stock cylinder head, send it to S&S, and we will basically punch the guides out, put new guides in it, CNC the port, CNC the chamber, deck the head, and put it into a configuration that is all ready to go for performance. Basically, you're getting our cylinder head without buying the whole head, and of course it's much more affordable than a head. You're looking at $950 versus a whole cylinder head, depending on options, could be as high as $1,400. So what we do is cylinder head would come in. Basically, I have a stock cylinder head here. It's of course got carbon in it, bore. It's going to have oil all over it. Still has the springs in it. We pull all the stuff down, discard the valves and springs, and inspect the head to see that it is acceptable. Like if the head's already been decked, of course it won't work for our service because the material is not there, and so we wouldn't be able to maintain the chamber size that we're looking for. There's all kinds of criteria that maybe you got stripped threads, that kind of stuff that we need to be aware of as we are clamping them on our fixtures, that kind of stuff. So we'll inspect the head, and then we get the head disassembled. We'll put it in our CNC machine. They'll port the intake and the exhaust. When it comes off the CNC machine, basically it's going to look very similar to this, minus the guides. Okay, the transition, through the bowl and seat area when we cut the seats will blend out, and you can see that not all of the port will clean up, and that's perfectly fine, because the reason for that is we can't control the castings. The castings kind of float around and don't maintain the tolerance that you do with a CNC machine. So it's perfectly normal to see a port that doesn't clean up. Now, like this exhaust port here, there's a lot of material in there that hasn't cleaned up, and that's okay. I guess what's important is that it cleaned up in and around the bowl area here, and we don't have big steps and misalignments. Okay, some more information about the ports. When we did these ports to put a 1/900 intake valve in here, we leave the seat alone. It's a stock seat. We just cut it bigger and sink the valve. And then the ports, when we developed the ports, we tried to keep them as small as we could. And that's kind of how these are a lot different than our standard port, in that this port is very small for the valve that we put with it. So what that means is, of course, you're trying to get more air through a smaller area, and that equates to more velocity. And velocity is key. You can't have too much, but the high amount of velocity, of course, creates more turbulence and therefore better combustion and more power. So we're getting more air in for the size of valve with a smaller port, and that equals better turbulence, better velocity, and more performance. In a nutshell, that's pretty much what we have. Now, when the guides go in, we have a manganese bronze guide, not just a soft bronze, but the manganese certainly gives this material some wear properties that are much superior to just standard bronze. And you can see on this guide we have an O-ring seal that when we put the guide in, anytime a guy services a guide, there's a chance for that bore to of course have gall marks or lines in it that of course oil can get through. So when you put in a replacement guide, it's a very good idea to have a seal on there so that we make sure we have a good seal and we don't get oil into the chamber and then into, of course, the ports. So we have two different guides. We have an intake and exhaust, and you can see that the radius on the exhaust is certainly tighter than what it is on the intake. The intake's got a nice long taper to it. On top of that, we put the guides in. We have a Viton seal here with a spring on the top to retain it. The underside of the seal basically mates with the guide that has I don't know if you certainly can't hear that, but there's a ridges on the guide that retain the seal, so they lock together and the seal doesn't come off. Moving on to, once the guides are in the head, we would assemble them with our valves. About the intake valve, it's a 1/900 valve. The stock one's about 100,000 smaller, And the exhaust valve that we have is, of course, the 1.615. The stock one's 1.575. So we're putting bigger valves in there so that we can get more air and of course, in and out. On top of those valves, when we get them in, we have a couple of different options on springs. We have a 585 beehive spring, and we have a 650 beehive spring. The difference there being, of course, this smaller spring for a smaller lift, and of course a lower seat pressure. This one runs around 125 on the seat pressure. The 650 spring will run around 170 pounds on the seat. So the reason why you'd want to kind of look between these two is if you're looking for a quieter engine, you're going to want a little less seat pressure. It's a little easier on the valve train. If you can stay below 585 lift, this certainly is the spring of choice. For the guys that want more lift and more performance, maybe you're not going to put the kit together the way we intended it to. You want to go even higher on compression for whatever reason. We certainly offer the spring to get the job done. So in a nutshell, that's how we do our step 4 and what the heads will have performed to them when you receive them back. Okay, now that we've completed stage 3, we've brought the bike back over here, put it on the lift and tore it down. We got the rocker boxes off, the exhaust off. We're going to replace the stock heads with the CNC heads. I'll start by removing the front head here and get the CNC head. I'm going to need a new head gasket. Okay. Here again, applying assembly lube to the bolts. Under the head as well as the threads. And of course the torque sequence is the same for these as it was for the stock heads. There's 2 steps. On the first step you go 12 foot-pounds, 17 foot-pounds, 90 degrees. And then you untorque them and then retorque them 12, 17, 90. And then move on to the rocker boxes. So I'll go ahead and torque them out this time. Okay, 12 foot-pounds. Again, 17 in the sequence. Starting on the primary side, the lowest bolt or outermost bolt, and then crisscrossing over to the cam side. And now we need to do the 90 degrees. I switch away from my torque wrench and go to a long ratchet. I'm going to mark my bolts so that I can see how far I've turned them with a Sharpie. Of course, you can use some brake cleaner and a rag to wipe off the marks on the head bolts if they're external, like the ones over on the drive side are. And now I need to back them off and retorque them again. There's 12 foot-pounds, now 17. And again, 90 degrees. Front head is ready for the rocker box. We'll go on and remove the rear stock head and put on the CNC rear head. Okay, now that we've got the rear CNC head installed and torqued, we're going to move on to installing the rocker box on the front head. So the first thing is of course the gasket. Okay, and these beehive springs, beehive being that they have a taper at the top in the shape of the spring. The old dual spring versions were rather large at the top, and so when you put a performance spring with the stock rocker box, you used to have to clearance inside here so that the springs didn't hit the rocker box. Well, the advantage of the beehive spring, one of the advantages, is that you don't have to clearance the stock rocker boxes, so we don't have to be concerned with that here. All right. Install these 4 bolts. 4 short ones and 2 long ones. Now I'm going to remove the old O-ring from the rocker box here because we have a new one supplied with the rocker box gasket kit. Clean some of this oil out of here and install a new O-ring. Okay, the next thing I'm going to do is, notice I didn't tighten these down because the rocker box can still move ever so slightly, because I want to make sure that all these other holes line up and that the bolts start nicely, because once you get these tightened down, if it's shifted a little bit, the bolt won't start nicely, and it's much easier to cross thread a fastener when you don't have things loose and easily alignable. Okay, before we put the rocker support in, there's a couple of gaskets that we need to replace on it, and they're underneath here in this breather cavity. Basically, you have a top plate, and there's a gasket here in between underneath that plate. Then you have a reed valve breather assembly. It has a little like Scotch-Brite pad underneath it, and underneath there you have another gasket. So we're going to put a new gasket in both locations, and then we'll set this all back into place in the rocker box. Okay, we're going to put the rocker support back in to the bottom rocker cover. Get all the bolts started here. And the beauty of adjustable push rods is that we don't have to have them in place right now because they collapse and can be installed after the rocker box is on. So I got all these bolts started. Now I can start to tighten down the base first, and then I'll work on the rocker support. The gaskets for this breather were included along with, so you get in a rocker cover gasket set, you get the base gasket, you get the breather, the 2 breather gaskets, you get that O-ring underneath there, and then of course you get the top cover rocker cover gasket as well for the front and the rear cylinder. Okay, I'm going to torque these bottom bolts, 5/16 fastener to the spec. Okay, the base bolts are tight. Now I can go on to the rocker support.
Okay.
Okay, now that the rocker support is torqued, we're going to put on the rocker cover. Since the stock valves are not in this assembly, that the rocker cover will need to be clearance checked. Because the valves, of course, are bigger, we had to sink them farther in the head, so that means that this rocker arm is actually rotated higher in the rocker cover. So what can happen is there's a rib inside the rocker cover that should be clearanced to ensure that the rocker arms do not hit the rocker cover. To check the clearance of the rocker arm to the rocker cover here, to make sure we have enough, I put a piece of modeling clay in here, and I'm going to set the cover on there without the gasket, and we'll see how close the rocker arm is to the casting. Okay. I'm just using my fingers to kind of center the cover on the base. And lift it back off. Okay, now you can see where the rocker arm is getting really thin to the clay. What you can do is just take a razor blade and cut the half of the clay off, and you can see how thick or thin the clay is to the casting. This one here we had 60 to 70 thousandths. We maybe didn't have to clearance it, but we did just to be safe. But for sure, it's something that you need to be aware of when you're assembling an engine like this with a performance part. And depending on the combination of parts, of course, that clearance can be less or more. All right, this gasket has to go a certain direction. As you can see over here, there is like a indent in the pattern, whereas this side is straight. So make sure you have the gasket on the right way. I have my clearancing in my cover. Mainly the clearancing that we just went through showed you the clay, the before and the after. The rocker arms clearance is generally, the intake is always closer than the exhaust, so on this one I didn't necessarily have to do the exhaust. I could see that it was way lower. Certainly not a bad idea. The time when you're really going to run into trouble, of course, is anytime a valve has been sunk, which in this case that has happened. But if you were to go with the 650 lift combination and put in an aftermarket rocker arm, anything over 585 lift, we recommend a roller rocker to reduce the friction at the valve stem interface. So when you go to that roller rocker or aftermarket arm, it may be a beefier component than the stock rocker arm, and of course interfere with the cover even more severe. So the last thing here in the rocker box is these top bolts. Of course, make sure you got your Loctite. You want to definitely start all of these, if not get them all snug, because the nature or geometry of this part is such that it has this slanted cover. So the second you tighten one of these down, the slant wants to make the part move that way. And so when you tighten one of them, consequently every one of these bolts gets the cover thrusted against it, so it makes them hard to turn in. So just kind of get them all drilled down as close as you can, and then go ahead and go through the torque sequence. Start in the middle, work your way out, and torque them up. Okay, I'll torque them up.
They say it's not bragging if you can prove it, and proving it is just what we set out to do in this video. After all, proving performance is our motto here at S&S. Throughout this video, we've been using a dynamometer to show the increase in performance for each step of the S&S 4-step process. We think it's important at this point to talk a little bit about what a dyno is what it does, and what it doesn't do. With this information, we believe that our customers can make more informed decisions about their performance purchases, and most importantly, be satisfied with the results. First of all, there are several types of dynos, but the most common type is the chassis dyno. If your motorcycle shop has a dyno, I can almost guarantee it's going to be a chassis dyno. You can just roll your motorcycle up the unit. Within a few minutes, you know how well it's performing. The basic models measure torque and horsepower by recording how quickly the rear wheel of the bike can accelerate a very heavy steel drum. Torque and horsepower are calculated based on how fast the dyno spins up. More advanced models have a brake that allows us to put a load on the motor at a steady speed. The dyno we use is a DynoJet Model 250i, which has an electric eddy current brake to load the motor. It's also equipped with an exhaust gas analyzer and air-fuel ratio meter. This is required for EFI tuning, so we've been using the dyno to measure horsepower and torque. But what are they? Which is more important? Torque is defined as a twisting force that can cause something to turn. In this case, it's the ability of your engine to turn the back wheel of your motorcycle. Torque is expressed as the amount of force applied multiplied by the distance from the center of rotation. Pound-feet is the correct unit of measure for torque, but we usually refer to it as foot-pounds. A good way to picture torque is to imagine that you are trying to get a rusty lug nut off your car. You can only exert so much force on the lug wrench, and hopefully it's enough. If not, you can put a long piece of pipe on the handle and get the nut off. You increase the torque by increasing the distance from the center of rotation. You didn't get any stronger. The other solution is to get your big pal Bubba to apply some more force. Whatever it takes to get your nuts off. So torque measures how hard you can turn your back wheel. Torque is therefore what determines how quickly you can accelerate. Whether they realize it or not, torque is what most street riders are really looking for. With a high performance upgrade, we are going the Bubba route. We increase the amount of force available to turn that wheel. Horsepower is mathematically related to torque. Torque multiplied by the engine RPM, all divided by the constant 5250 equals horsepower. That's why the torque and horsepower curves always cross at 5250 RPM on the dyno chart. The values will always be equal to 5250. Power is defined as how quickly work can be done. How fast can you move your 750-pound bagger from point A to point B? While torque determines how fast we can accelerate, horsepower determines our top speed. So is it more important to be able to accelerate to freeway speed quickly? Or is it more important to be able to hit 130 miles an hour? If I'm not on the drag strip, I'll go for acceleration every time. Another thing to consider is the RPM where horsepower and torque are produced. An engine that makes a lot of torque at 2500 RPM will be more fun to drive on the street than an engine that makes a lot of horsepower at 6000 RPM. Ask yourself this, how often do I run my bike at 6000 RPM? Unless you're a pretty serious racer, the answer may be never. We've done some dyno testing, so let's talk about interpreting the dyno numbers. First of all, you have to realize that dyno results are all relative. Unfortunately, the dyno gives you a number and people tend to think that that number is an absolute. The problem is that the list of variables involved in a dyno test is huge. So dyno results have to be accepted with a certain tolerance. Values from two different dynos will not be identical, and values from the same dyno may vary over time. Other factors include tire pressure, engine condition, engine temperature, barometric pressure, air temperature, humidity, how well the bike is strapped down, etc. The computer in the dyno attempts to correct for environmental conditions, but our experience has shown that they are still a factor. If you put more air in the rear tire, the dyno will show higher numbers. Bogus, but higher. We found that putting a lighter rear wheel on a bike will give us a few more horsepower. Is that cheating? Not if we use the same wheel for all of our tests. We discovered that if the flywheels in the engine are out of true, it can cause the engine to produce less peak horsepower. These are the kinds of things that can cause results to vary. With all this in mind, we try to reduce the variables in our testing at S&S. We have a standard procedure for dyno testing that we feel makes our results as honest and meaningful as they can be. If at all possible, we try to use the same motorcycle for testing a certain product. We always try to use the same dyno and do the testing within as short a time as possible. Tire pressure, the way the vehicle is mounted on the dyno, what gear the bike is in, and a number of other things are standardized for all our tests. That eliminates a lot of variation. A baseline run is done before we install our products, so we can compare our results to stock. Ideally, it's the same bike on the same dyno, so the only difference is the performance of the engine, because that's what we are really interested in. How much more power did this engine make after we installed our parts? So, will you get exactly the same numbers if you install these parts on your bike? Probably not. You may get less, you may get more. The important thing is to do before and after tests to determine the percentage of increase. It's also important to know that if you substitute components in your performance package, all bets are off. Let's say you choose another exhaust system because it looks cooler or because it isn't as noisy. You can't expect the same results. Exhaust systems that are designed for style sometimes are not designed for optimum performance. And performance exhaust systems are often pretty loud. We are comfortable recommending our components in the S&S 4-step process. We know what the combinations are, and we've tested them. We have proven that they will perform. So we're back to that proven performance thing again. No brag, just fact.